Hello, this is the Tepid Coder. In this episode, I want to talk about variadic template functions. So in the past, I've talked about how to do variadic functions in C, but, traits. Those are kind of unsafe. I'm going to give an example of how they might be unsafe. So, the easiest example I can think of why they might be unsafe would be if you have something like some function foo, it's a templated function. Let's say you have to pass it a count. So I pass it like 3 is the count, and I pass it 1, 2, 3, right? Later I come on, and I say, I actually need an extra argument here. I want a 7. Well, maybe I forget to put the 3 here. That 7's not going to be used, so I'll have to track down one wrong there, why it wasn't being used. Or maybe I delete a couple of them, and I still have a 3 here, because I didn't really keep it in track. I forgot to fix that first argument, or I didn't make it the right value for some reason. And I was trying to pull more arguments from the stack than actually exist. So that's a problem. These can be out of sync. I don't like that. But maybe I get this right. Maybe I add a third argument, and I'm like, okay, I want it to be 1.2. But it's expecting all integers. That's an issue, right? So it's not actually giving me type safety. The other thing is, too, if you use a function like printf, you could be doing stuff like percent sign, let's say, pri i64, right? And then we have another one, another integer, pri i64. Okay. Oops. And then we're going to say, I don't know why I'm putting commas there. Anyway, percent sign f, right? That's the right way to specify this. If it's a float, it just gets coerced into a double. And same thing if I do like an extra one, 3.14 or something. That's actually literally a double. Those are both percent sign f. But I don't need to know that, right? If I'm doing this in a way that automatically detects a type. So that's going to be the advantage of the C++ template functions. So let's actually create that. First thing I want to do is I want to say template type name t. So it's going to have some templated argument. The type I don't know, it's unspecified. Then I have another type name. I'm going to call it targs. And what you do is for any extra arguments you have, you do ... targs. And that means any number of arguments can be here. You can actually put these in front if you want. And then if I did that, say I like type name front arg or something like this, that would actually let me do something like, I don't know, let's give this a name first. I'm going to call it show types. It'll return void. Okay. But if I call it show, try it again, show types with like, I don't know, ABC, then 1, we have to pretend this part doesn't exist, right? In that case, it would know this last type right here is just going to be whatever. It could be deduced, and these are actually going to be the variadic types. It doesn't really matter which side I stick those in. I could even have like a type in the front and type at the end too, so type name, or I can put like, let's say int right here, right? In that case, there's some integer right here. So it knows everything between this integer and the final argument are the variadic ones. So you can do all kinds of things like that, but I'm going to keep this real simple for now. I'm going to have it be just a type name, and then it's going to be a bunch of packed parameters. So let's do that. And the first thing I'm going to do is just show the types that are passed, just to show it works. So I'm going to have a t, let's call it t value. I'm going to have targs, ... let's say fargs for function args. And then what do I want to do? Let's actually say standard cout. I'm going to say type of argument. Okay. And what you can do is you can say type ID, pass it a type. T is the type. We don't know what it is. We could say .name. That'll actually give me some kind of a string for the type. So like if it's an integer, it'll be an I, like this, right? If it's a float, it'll be an F. If it's a double, it'll be a D. If it's a, I don't know, like const char string, it's just going to give me a C. At least on G++ that I'm using right now. This is like implementation defined. And if you use Boost demangler, you can actually get the full qualified type from that type ID. Anyway, right now it's only going to show what this first argument is. If I want to use the rest, I would have to actually call the function again and push the packed arguments into the first. So if I do this, show types, and I do fargs ... that's actually going to expand the remaining arguments. So I'm going to kind of write it out so you can see it a little better. So show types. Let's pass it a const character pointer. I'll say test. That's a const char star. Let's pass it an integer. I want -3. How about it's going to be an int? And how about a floating point? I'll say 5.6. That's an f, so a float. And how about 2.14 with no f at the end? Means double by default, so double. So what's going to happen the first time I call this is t value is going to be this first argument, and the packed arguments are going to be these three. They're in this. Okay, so it's going to show the type, which should be a C for character, at least in this compiler. Okay, then it's going to call show types again with the remaining arguments. Well, the remaining arguments are the packed ones right here that I'm expanding with the dot. So this right here, fargs, it becomes this. It'll be -3, comma 5.6f, comma 3.14, right? It becomes that. Okay. So that means the next time I call it, this 3 right here is going to be the t value. It's the integer. It's what it's going to print out. It's an I on this compiler. And the next two that are packed are going to be these two. So now when it calls it, it'll be 5.6f, comma 3.14, which means the t is going to be this 5.6f, and then the packed arguments is just this one, 3.14. Okay, so it prints out an f for floating point, right? And then it's going to call it again, and all we're going to have is 3.14 with no extra arguments. Now this is going to be a problem, because when it tries to actually use this, it's going to try to pass 3.14 as the t, and then nothing as the extra arguments. So when it actually deduces the template, it's going to be a problem. I want to show that first before I do anything else. So I'm going to say g++ test.cp-o test, if that works. So you can see recursively required from here. And it's going to say no matching function call for show types. Candidate is this, takes a type t plus some packed arguments. And it says template argument deduction or substitution failed, expects at least one argument, 0 provided. So 0 provided, because when it finally called the last time, there were no arguments. So what you can do to get around that is you can say if constant expression, so at compile time, evaluate this, size of ... That's a new type of size of that works on these type of variadic templates. I can say frg, true function arguments. So if it has a size, which the size is always going to be equal to the number of arguments passed, each call, I'll actually even print that out. Standard out, I'll say unsigned int size of ... fargs. Okay, end of the line. I'm going to say, I'll bring that down to the next line. Variadic arguments were passed to the function. I'm going to reorder that. Let's say, come on. Yeah. So that many were passed to the function. Yeah. And then it'll call itself, like I showed here, with less and less until there's none to pass. So that should work. Let's give that a try. You can see that worked. Print it out. Okay, you can see we have C for the constant character pointer. We have I for the integer, F for the float, D for the double. Now, that's cool that I can show these types out, and I could even do some if statement on these like type IDs or whatever to maybe determine at runtime what to do with them. But you can do even better than that, especially since this type ID is going to be implementation defined, so per compiler is going to be a different string it gives you when you call this .name on it. So what you can actually do is you can say if, I'm going to say const XPR, constant expression, so evaluate this at compile time. So if, let's see, standard is floating point, and I give it the type t value. So if it determines that this type right here, the first argument passed, is floating point type, which would be a floating point with a float or a double. So if float or double, we're going to do this. Standard cout. This is a floating point type, I'll say. Let's do 3 of these. So else if is integral. Integral type. So this is an integer type, I'll say. Otherwise, for the constant character pointer, I'm going to say is same this const char star. You can use is same for any type, but this like integral, this floating point, they have a bunch of overloads for things like I don't know, int, unsigned int, probably things like uint16t. I don't know if those actually work. If not, I could always do is say make sure that those work. Okay, I'm gonna say this is a const char pointer type. So do an else if here as well. Oops, else if. Let's see if that works. And it does. Okay, so let's use this as a constant character pointer type. Okay, there's 3 variadic arguments left. Next type we can see is an int type ID. It's an integer type. Detected it properly. There's 2 variadic arguments passed the function now. Okay, first one is an f, floating point type. Cool. Now there's 1 variadic argument, plural there, that's kind of funny, passed to the function. Type of the argument is d, which is also a floating point type. I don't like that there's like no space here, it's kind of bothering me. So why don't I fix that real quick. And argument versus arguments is kind of bothering me too. So I'm going to fix that as well. Let's say argument. Okay. Let's get rid of that. Yeah. Let's drop this down. I'm going to say size of dot 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 f_args greater than 1. You know, in fact, not equals 1. It would have to be greater than 1, though, for this to be true. Doesn't really matter, whatever. Yeah, so if it's not 1, then read an S. Otherwise, put nothing. We'll see if that fixes it. Okay, invalid operands. Const char 1, const char 30. Okay. Doesn't like that, huh? What if I do this? Now it's happy. Okay. So we have 3 variadic arguments. We have 2 variadic arguments. 1 variadic argument. Much better. Anyway, so that's pretty cool. I want to show an example of how this could be useful to use in a real project. Why you'd actually want to be able to detect this at runtime and be able to use this. And I'm going to show an example of that in the next video. I think people will really like that. It'll be useful in like an actual production case, I think. Because I use it for that anyway. Anyway, if you like the video, give it a thumbs up. Consider subscribing for more content like this so you're aware of when it drops. And thanks for watching. So, drop any comments you have, any suggestions, any questions, and I'll get to those. And I'll catch you guys later.